So for our next topic, we're going to be looking at heat exchangers. So this diagram up here is of a co-current heat exchanger, which basically means the two currents are going to be flowing in the same direction. So we have a hot current and a cold current, and there will be some heat transfer rate, dQ, as the hot stream will lose heat to the cold stream. And so basically what we have here is like a temperature profile diagram. Both streams will enter with some initial temperature in the inlet, and both will exit with some outlet temperature. And as you can see, the cold stream gets heat from the hot stream, and the hot stream loses heat to the cold stream. And so delta T1 is going to be the difference between the two temperatures of the inlet streams. Delta T2 is going to be the difference in the outlet streams, and delta T is going to be between the two streams at any point. So basically what we want to do is we want to describe equations for this dQ for both streams. So for the hot stream, we know that it's going to be losing heat, so we're going to have a negative. And it's going to be the mass transfer, or the mass flow rate times the heat capacity of the hot stream times dTH. We're going to do the same thing for the cold stream. So dQ is going to be this time positive. The mass flow rate, heat capacity of the cold stream, dTC. And if you see, we have this CH and CC here. And what these are basically going to be the heat capacity rate. So the heat capacity rate is going to be equal to this m dot times C. So we're going to say this is equal to CH dTH, and this is going to be equal to CC dTC. So now what we want to do is we want to make some equation that will take these both into account. So we're going to do that with a dQ equation. So the change in the heat transfer rate is going to be equal to some heat transfer coefficient, U, times the change in temperature over the differential area. And so we're going to use the delta T from here. So delta T is going to be equal to TH minus TC. And then what we're going to do is we're going to take a derivative of this so that we can sub in the dTH and dTC. So this will give us d delta T is going to be equal to dTH minus dTC. And so now what we can do is solve these for dTC to dTH. So this is going to be dTH is equal to dQ over CH, and dTC is going to be equal to dQ over CC. So now we want to plug these in here. d delta T is going to be equal to, we're going to take out a dQ times 1 over CH minus 1 over CC. And so this is a formula that we're going to use to be able to combine two streams into one and convert them using some heat transfer coefficient. So now that we've derived these two equations, you see we have a dQ in each, and so we can combine. So that leaves us with d delta T is equal to, I'm actually going to take out this negative from the 1 over CH minus 1 over CC. So the negative is going to come out front. That's going to be U delta T 1 over CH plus 1 over CC dA. And then I'm actually going to move the delta T over to the other side. And now what I'm going to do is I'm going to integrate from position 1 to position 2. And as you can see, none of these have to do with the area, so we're going to take them out. And we're just going to call the area over which we lose heat just A. That's the total area from 1 to 2. This is going to be equal to the natural log of delta T2 over delta T1. That's because the integral of 1 over delta t is going to be ln of delta t. So now that we have this, we want to get rid of these ch and cc values, because in the end what we want is an equation in terms of q. So we're going to relate this back to q. So the total heat transfer from the hot stream, q, is going to be equal to negative ch dth. And so just to expand this a little bit, this is going to be equal to negative ch times th initial minus th outlet. And so to get the ch on its own, we're going to have ch, or actually we're going to have 1 over ch, because that's what we actually want to plug in. So we'll do 1 over ch is equal to negative q times th, or it'll actually be thi minus tho all over negative q. And we'll do the same thing for the cc, and in the end we'll get 1 over cc is equal to tci minus tco all over q. So now what we need to do is plug these both in. This will give us ln delta t2 over delta t1 is going to be equal to negative ua times th. And what I'm actually going to do is distribute this negative, so it's actually going to be th0 minus thi all over q plus tci minus tco all over q. And so now I can take out this q, move it out front, and it'll leave us with the equation ln delta t2 over delta t1 is equal to negative ua over q times th initial, or th outlet minus th inlet plus tc inlet minus tc outlet. Now I'm going to erase some stuff and get some more room so we can continue. So now that we've derived this equation up here, it's time to rearrange some of these temperature values. So we have ln of delta T2 over delta T1 going to be equal to negative UA over Q of THI minus TCI, that quantity minus THO minus TCO. And so what this does is it makes it able for us to sub in delta T1 and delta T2 for THI minus TCI and THO minus TCO respectively. So that'll give us ln delta T2 over delta T1 is equal to negative UA over Q times delta T2 or delta T1 minus delta T2. So now we can do a little rearranging and get an equation, solve for Q, which equals negative UA delta T1 minus delta T2 over the natural log of delta T2 over delta T1. And from here we can do a Taylor expansion series to prove that it is equal to the counter-current heat exchanger and also the co-current heat exchanger. Alright, so now that I have this equation, I'm going to first of all distribute this negative sign into this delta T1 minus delta T2. So that's going to give me Q equals UA minus delta T2 minus delta T1 all over ln of delta T2 over delta T1. And if this term right here looks familiar, that's because that's the log mean temperature difference. So sometimes referred to as LMTD. This log mean temperature difference is basically just the average of delta T1 and delta T2 using the logarithm scale. So the formula for log mean temperature difference is A minus B over natural log of A over B. So you can see we have that same format here. And by the definition of this, that is going to be equal to E minus A over ln of B over A, because it's simply an average. So, by knowing this, we can say that Q is equal to UA delta T2 minus delta T1 over the natural log of delta T2 over delta T1, and that's going to be equal to UA times delta T1 minus delta T2 over the natural log of delta T1 divided by delta T2. And so this just proves that the co-current heat exchanger and the countercurrent heat exchanger will exchange heat at the same rate. However, using the countercurrent, we're able to get the hot stream down to a much colder temperature because the two outlet temperatures do not converge on each other. The outlet temperature of the hot stream will converge on the inlet temperature of the cold stream in a countercurrent, which is why they're better in real practice.